Students, now we are going to do part 5B. 5B is add a PI controller to the system model. 5A, sorry, we are going to do 5A, add a PI controller to the system model. Plot the root locus of the system with PI controller using MATLAB. Both KP and KI should be included. Okay, this is the first part of 5A. And the second part is also plot the root locus of the system when KP equals to 0. This means you are only using the I controller. Okay, so this KP is going to be 0 in the second part of 5A, and there is going to be only KI in the second part of 5A. Okay, so first we are doing first part of 5A, and in the first part of 5A we will have the same thing. Okay, like in 4A, so we have this plant, and this is actually the closed loop transfer function of the plant, and this is what we got. Okay, it's the same like this portion, this portion is same. And then you have this plant, and now you are going to add this PI controller. This is KP plus KI over S. This is PI controller, and this is the feedback. Now we are going to just simplify this PI controller. So this is KP plus KI over S. So you can take the LCM and then take this KP common. When you take the LCM, you will have S over here, and when you will take this KP common, you will have S plus KI over KP, and KI over KP is what we are going to say that it is Z. Okay, we are going to assign it a different variable named Z. Okay, so now what we are going to do, we have the Z. So KP S plus Z over S. Remember, this is actually an extra zero. Now, when you only have KP in the proportional controller, you only have what? KP. Now, when you have proportional integral controller, you have introduced a zero at S equals to minus Z and a pole at S equals to 0. This is the difference actually. So you have added a zero and a pole in your root locus, or you have added a zero and a pole in your system when you have added an integral controller. Now you are going to choose a small value of Z. So you will choose the value of Z between 0 and 1. This is normally done. Okay, we do not want that our 0 is far away from pole. If we choose any value from 0 to 1, because we know that our pole lies at S equals to 0. So we do not want our 0 to be very far away from the pole. So we want it to be very close. So we are going to choose any value between 0 and 1. So for example, I am choosing Z equals to 0.5. You can choose any other value like Z equals to 0.3, 0.6, 0.7. You can choose any value. Okay, so every group will have different value of Z. Now, what your PI controller is going to look like, it is going to be KP S plus 0.5 because I have chosen Z equals to 0.5 over S. Okay, so now we are going to substitute this. This is the PI controller, this is the plant, and this is our feedback. Now, remember, same like in P controller, uh, the PI controller, when we want to make the root locus, we have to consider the open loop. Now I am going to come to the MATLAB, and this is the MATLAB. Again, CLC, same thing. I have taken KP1. KP1 means you are not considering KP to be there. And you can consider Z equals to 0.5, like 0.5. Okay. And this is transfer function 1, 2, 3, 4. Everything is there. So you can choose any value between 0 and 1 for Z. And this is the closed loop transfer function of the plant, which is actually this part. Okay, this part is closed loop transfer function of the plant. And then you have the PI controller, and in this PI controller this is KP 1 plus Z comma 1 comma 0. So this means this 1 comma 0 means S, and this is S plus Z, and this is multiplied with KP, as you can see from here. Okay, KP is multiplied with 1 plus Z. Z is 0.5 divided by 1 plus 1, sorry, KP 1 space Z, which is Z is 0.5. So this is going to be S plus Z, and at the denominator you have 1 space 0. 1 space 0 means S. Okay, so we have already done this in MATLAB. Now right now we are doing PI controller. So what we have, we are going to write PI over there. Okay, this is PI controller, and PI controller is multiplied with the plant, so you will get the transfer function system open loop. Okay, keep this value of KP 1. Okay, so KP should be taken over here as 1. So where is KP? KP is taken as 1. Okay, why? Because we do not want this variable to, because this variable doesn't have any effect on the root locus blossom. Okay, so you can take 1, 2, 3, any value, doesn't matter. And you are then going to run it. When you run it, now you get this graph. Now look at this. This is the same. This portion is same, 152, 134 as in part 4a. So this portion is same. This portion is same. Minus 152 minus 134. What is the difference? This is the difference. You have added a pole and a 0, and look how close the pole and 0 is. Okay, so you have added. Now by adding a pole and a 0, this is not going to make any difference, but this has a little bit of curvature. It's not, straight, vertically straight. It has got a little bit of curvature, and this curvature has actually reduced the steady state error of the system. But if you have a straight line like that, you will not be able to reduce steady state error. But if you have a little bit of curvature, this curvature is going to reduce the steady state error. Okay, so this was actually first part of part number 5a, in which you have to consider both KP and KI. Okay, now the next one is going to be, the next is about also plot the root locus of the system when KP is equals to 0. Okay, so I controller is only used. So this means you are not going to consider KP now. So this means you will take KP equals to 0. Do not put KP 0 over there. If you put KP 0, what's going to happen? This whole thing is going to be multiplied with 0. And when you have the numerator thing 0, the denominator is actually S. This is S. Okay, this thing is S. And this thing is, if this whole thing is 0, 0 divided by S is 0. So you will have nothing. So what I will do, I will remove this. I will put a percentage sign over there. And I will say that this is my I controller. So in I controller, what it is, when KP is 0, okay, come here, come back here, use this equation. When KP is 0, what you have? KI over S. Do not use this form, because if I put KP equals to 0, this whole thing is going to become 0, and 0 divided by S is 0. So I do not want this whole thing to be 0. So what I will do, I will use this form, and when KP is 0, I will have KI over S only. So I will have KI over S. So this means I will have KI in the numerator, and this portion is S. Okay. So choose the value of KI1. Okay. Choose the value of KI1. When you take KI1, this means KI is not considered. Okay. This variable is not considered. And then you have this one, I controller. So put an I controller over here. This is I. So look, they both are same. And then you have this transfer function open loop. And when you run it, look how the graph looks like. Now this was actually the pole S equals to 0. And look, because there is no 0 now over here, so it's not going to stop here. It's going to go to infinity. And when this goes to infinity, this was what? This is what? This is minus 152 plus 134. It's the same thing, but because it's moving like that, it has moved this like this. Okay, now it is not going straight up and down, but it is, bending. So what has happened when I have made KP 0? So it has bent. So this is actually the root locus of only I controller. Okay, remember all the 3 poles. There is one pole over here, another pole over here, third pole over here. When I move a pole, now this doesn't give me an option. Okay, this is what I'm doing. I'm moving the pole. When I move the pole which is over here and the pole which is over here also move. It's not that only one pole moves, because when you change the value of gain, the value of gain changes for this one and for this one as well. So all the three poles move together. As I'm not able to show it to you over here, but remember all the three poles move. So it is at 0, it is at 4.94, so it should be at 4. So it is, this pole is going to be somewhere over here. Again 4.94. Where is 4.94? 4.94 is somewhere over here. This is 4.9. So this means when one of your pole is here, other pole is here, the third pole is actually over there. So all the three poles move simultaneously. Remember this thing. And what is going to happen when your pole is going to come over here? Your system will become unstable. Some students told me that my system is becoming unstable when you do part 5b. Some student complained that their system is becoming unstable at ki value 12.6 or something greater than. Look, when the gain is at 12.7 or it is at 12.6, what is happening? You are crossing this left half plane, and when you cross this left half plane and you come to the right half plane, when your roots come to the right half plane at 12 equals, at gain equals to 12.9, which is actually ki. This gain is actually ki. Remember this thing. When ki becomes equal to 12.9, look, you have entered into the right half plane. And when you have entered into the right half plane, this means your system now will become unstable. So if you are in the left half plane, your system is going to be stable. When you move to the right half plane, look over here, 10.2, stable because you are in the left half plane. When you come to like 10.11.6, still you are stable. But when you come to like 12.2, you are actually at the boundary. And when you cross 12.5, you go to the right half plane. Okay. So in part B, you will have ki. You can, if you choose ki greater than like 12.5, you will see the instability. But that is okay. You can discuss that thing. But by looking at the root locus plot, you can tell that whether the system is stable or unstable. Okay. Thank you.